The Second World War was a conflict defined by staggering logistical demands, a sprawling global chess match.
Victory often hinged not on fire superiority, but on the ability to move men and material faster than the enemy. While the world remembers the names of generals and the clatter of tank tracks, the true unsung battles of this era were fought against the landscape itself. The most formidable enemy was frequently the terrain, the suffocating heat of the jungle, the paralyzing cold of the subarctic, the relentless power of the sea, and the sudden, unforgiving barriers of European rivers. Standing between these impossible barriers and the advancing Allied armies were the specialized units of the United States Army Corps of Engineers. These were not simply soldiers with shovels. They were mathematicians, designers, geologists, and mechanics, tasked with solving logistical puzzles deemed mathematically and environmentally intractable. They were asked to turn bog into highway, sea into harbor, and rock into runway. The first great test of American engineering grit materialized not under the heat of battle, but under the relentless, deep freeze of the subarctic. Following the attack on Pearl Harbor, the vulnerability of Alaska became immediately clear, necessitating a secure land-based supply route running from the contiguous United States up through Canada. The resulting project, the Alaska-Canada Highway, or ALCAN, was a monumental undertaking covering 1,700 miles of utterly hostile territory. It began as an urgent military necessity, but quickly devolved into a primal battle against permafrost and muskeg. The engineers arrived in the spring of 1942, greeted by a landscape that mocked conventional construction. This was a wilderness of immense proportions, marked by dense boreal forests clinging to an unstable foundation. The great antagonist was the muskeg, a vast, shallow, waterlogged bog covering the permanently frozen ground beneath. The engineers quickly learned that the muskeg was beautiful in its deceptive lethality. The surface, often covered in moss and scrub, appeared firm, but beneath lay a layer of decaying vegetable matter saturated with water and ice. A D8 bulldozer, the standard heavy equipment of the time, could be swallowed whole in a matter of minutes, its heavy steel treads turning futilely as the black, freezing mire consumed the machine. The key technical challenge was the permafrost, the permanently frozen ground. When the protective insulating layer of surface moss and organic matter was disturbed or scraped away by construction activity, the summer sun would inevitably penetrate the earth. This caused the permafrost to thaw, turning the solid ground instantly into a soupy slurry, known dreadfully as thermokarst. The frozen landscape became liquefied, swallowing any conventional road base poured upon it. This meant the engineers could not simply plow a road. They had to build a floating, insulated platform over the frozen ground without disturbing the natural insulation. The solution was a return to ancient methods, adapted with industrialized vigor, the corduroy road. Teams of black and white engineers and civilian contractors working side by side in temperatures that dropped frequently below 40 degrees below zero, devised a method involving layering materials. First, vast quantities of timber were felled and laid side by side perpendicular to the road's path. These logs formed a continuous floating raft, distributing the weight over the unstable muskeg. This layer was then covered with insulating moss and brush, acting as a crucial barrier to protect the permafrost below. Finally, gravel and graded earth were poured on top, forming a temporary yet functional surface. The smell of pine and burning wood mingled with the acrid scent of diesel exhaust in the frozen air. The work was non-stop, characterized by the mechanical drone of chainsaws, the grinding gears of trucks, and the constant chilling rush of subarctic wind. By November 1942, the pioneering road was complete, a barely traversable, meandering spine of timber and gravel. But it was a route, a steel artery punched through the impossible north, a foundational triumph of adaptation against nature's cruelest environment. Simultaneously, thousands of miles away across the Atlantic, naval engineers faced a terrain problem of an entirely different magnitude: the sea itself. The strategic imperative was clear: to invade occupied Europe via the Normandy beaches. But the success of that invasion, Operation Overlord, hinged entirely on logistics. Traditional ports were heavily fortified and situated too far from the front lines. The supply chain required a port capable of handling thousands of tons of material daily, but there was no port available. The challenge was to build a full-scale deep-water harbor on a shallow, exposed beach, a structure capable of weathering the violent unpredictability of the English Channel. The audacious answer was the Mulberry Harbors, arguably the single most fantastical engineering achievement of the war. These were not merely floating docks, they were two vast, temporary floating cities designed and constructed in secrecy across Britain, then towed across the Channel and assembled under fire. The very concept was grotesque in its enormity. The central components were the Phoenix caissons, colossal, reinforced concrete boxes, some weighing over 6,000 tons and standing as tall as 5-story buildings. They looked like monstrous gray sponges or immense, hollowed-out bunkers. The design was a masterpiece of compromise between weight and seaworthiness. They had to be robust enough to withstand the Atlantic's ceaseless battering, while shallow enough to be floated and towed. Once they arrived at the assigned sectors off the Normandy beaches, Mulberry A for the Americans, Mulberry B for the British, they were intentionally sunk in precise formations. The sinking created immense breakwaters. The process of sinking them was terrifying and precise, involving the controlled flooding of interior compartments. This turned the floating boxes into permanent, immovable defenses against the powerful tidal range and the crashing swells. The atmosphere during the assembly phase in June 1944 was one of high operational urgency, mixed with the constant vibration of nearby artillery fire. Tugs strained against the current, guiding the huge barnacle-encrusted caissons into position. The air tasted of salt spray and oil. The constant, wet roar of the Channel waves attempted to tear the structure apart. This provided a stressful soundtrack. The engineers, working on narrow gangways and exposed pontoons, battled the tidal range. The tide could fluctuate by 15 feet in 6 hours, complicating every alignment effort. Mulberry B, the British sector, comprised nearly 1.5 million tons of concrete. It recreated the physical geometry of a proper port, complete with protected anchorages and pierheads. Floating roadways, known as whale components, connected the pierheads to the beach. These whale roadways were ribbed steel laid across floating pontoons. They rose and fell dynamically with the tide, ensuring continuous unloading regardless of sea level. Mulberry A was largely destroyed by a massive, unexpected storm in late June 1944, a testament to the Channel's brutality. Mulberry B continued operating. It poured hundreds of thousands of vehicles, tons of ammunition, and millions of gallons of fuel onto the European continent. It was the crucial logistical linchpin that made the swift advance possible, a silent, concrete victory over maritime impossibility. The focus then shifted inland, following the mechanized spearhead of the infantry, racing across Western Europe. The advance was swift, often outrunning its supply lines. It hit an almost insurmountable obstacle, the wide, deep, and swiftly flowing rivers of Germany. The most significant of these barriers was the Rhine, a mile-wide, historical, and strategic waterway, fiercely defended by the remnants of the German army. Engineers were tasked with achieving the near-miraculous feat of bridging this massive barrier under continuous, intense artillery fire.
They had to do it in hours, not weeks.
The solution lay in standardization and rapid modular design, epitomized by two structural masterpieces, the Bailey Bridge and the Treadway Bridge. These steel structures represented a triumph of portable, interchangeable engineering. The material texture of this phase was cold steel. The smell was wet river mud mixed with explosive residue. The sound was the rhythmic clanking of thousands of steel pins being driven home.
The Bailey Bridge, designed by the British, was the heavy lifter.
Its design relied on prefabricated, standardized steel panels that could be manually carried by a handful of men.
These panels were pinned together to form larger girders and trusses.
The beauty of the Bailey system was its ability to be cantilevered outward from one bank.
It was rolled across the river on rollers and supported by intervening pontoon ferries or fixed piers.
The assembly was a high-pressure ballet of manpower and precision.
In the spring of 1945, at places like Remagen and Weasel, U.S. Army engineer battalions worked in shifts around the clock.
They sometimes fought off German counterattacks while simultaneously driving pins into bridge panels.
The Treadway Bridge, an American invention, was often used for the lighter, faster crossings.
It consisted of two continuous steel mats laid side by side, supported by inflatable or rigid metal pontoons anchored firmly against the powerful current. These were the critical steel arteries that allowed columns of trucks and medium armor to cross immediately behind the first assault wave.
The atmosphere on the banks of the Rhine during these construction efforts was one of extreme tension.
Searchlights occasionally crisscrossed the water, making the work visible to enemy spotters.
The engineers, wearing heavy woolen uniforms saturated with river spray, were driven by the understanding that every hour spent constructing the bridge meant time gained for the troops.
This time was gained for the troops advancing on the other side.
The engineers at the Rhine did not just build bridges, they fabricated functional arteries of war. They often achieved the seemingly impossible feat of erecting a stable, heavy-traffic bridge over 1,000 feet of fast-moving water in less than 36 hours.
This was a testament to the training, the design, and the sheer, focused technical grit of the men involved.
Far to the south, the war against Imperial Japan demanded a radically different approach to logistics. Focus shifted from cold steel and deep rivers to conquering the suffocating jungle density and tropical weather. The conflict in the China-Burma-India theater required vast quantities of war materials to supply Chiang Kai-shek's forces in China. The only land route was the Burma Road, a treacherous, narrow, winding path. It had been rendered nearly impassable by conflict, choked by landslides, and submerged under seasonal deluges. The mission was simple yet monumental: restore and upgrade the supply lines of the Burma Road through Burma, now Myanmar, and China. This project required mountains of earth and rock through torrential monsoon rains. This required the specialized expertise of engineering teams who were masters of earth moving in the most challenging climate imaginable. The environment was a sensory assault. The air was thick and humid, heavy with the smell of wet earth, rotting vegetation, and the metallic tang of sweat. Engineers and local laborers worked under a sun that baked the ground to a rock-hard consistency. Hours later, they were utterly transformed by the monsoon.
It turned every hillside into a cascading torrent, and every valley floor into a deep, clinging mud pit.
The ground texture ranged violently, from fine, powdery dust that coated everything in a blinding layer, to thick, viscous clay that sucked the boots off a man's feet and clogged the treads of every piece of heavy equipment. The engineering task was twofold. First,
fighting the landslides. They used explosives and heavy dozers to remove millions of cubic yards of rock and earth. And second, establishing proper drainage to stabilize the roadbed against the destructive runoff. They introduced extensive culvert systems and cut deep, reinforced ditches alongside the road. These were designed not just to move water away, but to channel the overwhelming volume of the monsoon without eroding the new road surface. The engineers deployed massive fleets of equipment, including graders, shovels, and rock crushers. Often, they had to maintain them with improvised parts in the middle of nowhere. The constant struggle was keeping the earth-moving operations going despite the breakdowns caused by dust, mud, and humidity. They learned to stabilize the road with layers of crushed rock, creating a durable, all-weather surface. This was capable of sustaining the continuous heavy traffic of convoys carrying fuel, ammunition, and vital supplies. The rumble of the heavily laden trucks, echoing through the dense, dripping jungle canopy, became the sound of the restored supply lifeline. The successful restoration of the Burma Road was a testament to unrelenting labor against the jungle and the climate. It transformed crumbling paths into reliable, high-capacity routes, ensuring that the necessary materials reached the far eastern front. The final, distinct theater of logistical triumph lay thousands of miles away across the vast sweep of the Pacific Ocean. The island-hopping campaign demanded the establishment of air superiority and the projection of heavy bombing power against the Japanese mainland. This required fully operational air bases, capable of handling B-29 superfortresses, the largest aircraft of the time, complete with long, durable runways. However, the chosen battlegrounds were remote coral atolls and volcanic islands. These landscapes were inherently unstable, uneven, or, in the case of coral, brutally hard but prone to fracturing. The engineers of the Naval Construction Battalions, the Seabees, were tasked with turning desolate specks of land into strategic air bases. These lands were rocky, scrub-covered, or composed of blinding white coral. Their ingenuity lay in their unique geology of the coral islands. The atmosphere of the Pacific bases was one of unrelenting heat, corrosive salt, and the ever-present, dazzling glare reflecting off the coral. The texture of the ground was either jagged, sharp volcanic rock or fine, crushed coral that was both blindingly reflective and incredibly dusty. The primary challenge on atolls like Guam, Tinian, and Saipan was creating the necessary flatness and length for heavy bomber operations. This had to be done out of the existing geography. The Seabees used explosive ingenuity to conquer the coral. Beneath the thin topsoil of many atolls lay immense deposits of hard, calcareous material, coral rock. It was too hard to grade conventionally, but too brittle to serve as a stable foundation without treatment. The engineers perfected the technique of blasting the coral using massive amounts of high explosives. This did not just clear the area, it shattered the underlying structure into a usable, compactable aggregate. Heavy machinery, scrapers, compactors, and steamrollers were then brought in. They crushed and rolled the pulverized coral into an incredibly dense, stable base layer. This material, often spread dozens of feet thick, provided the resilience needed for continuous heavy use. It was then sealed with asphalt or cement to prevent dust and erosion. The process was deafening, marked by the constant roar of engines. Also by the sharp crack of controlled explosions and the continuous rattle of heavy trucks hauling coral aggregate. In places like Tinian, the Seabees effectively erased the island's natural contours. They carved out what would become the world's busiest airfield, a network of 4 parallel runways. From here, the final, decisive bombing campaign was launched. The transformation of these tiny, remote coral atolls into complex, self-sustaining logistical hubs defined the final phase of the Pacific War. The engineers turned the white, dusty plains of coral into vital air bases.
They proved that no terrain, no matter how remote or geologically hostile, could stand against urgent necessity and focused technical mastery. These 5 monumental achievements, the forging of a highway through subarctic muskeg, and the erection of concrete harbors in the violent English Channel,
The instantaneous spanning of the wide Rhine under fire, the transformation of the suffocating Burma Road through the monsoon, and the flattening of sharp coral atolls into B-29 runways collectively redefine the limits of military engineering.
the U.S. Army Corps of Engineers and their affiliated construction units were the silent, essential drivers of the Allied victory.
They were the men who conquered the globe's most difficult terrain problems, ensuring that where the fighting man needed to go, his supplies would follow. Their work stands as a lasting legacy, built not of ephemeral victories, but of permanent steel, concrete, and rock.
Carved into the face of the earth itself.